let's take a look at a lot of the notions that we were studying when we were going over linear transformations of Euclidean space. We want to go over a lot of these notions now for an arbitrary vector space. So let's start with just a vector space V here. So V is going to be vector space. And then let's let V1 through Vn, we'll let this collection of elements of V be a subset. And then recall this definition that for another vector V in capital V, this vector is a linear combination of elements in the set V1 through Vn if there exists, say, these constants or scalars Ci, these are real valued, such that we can write V as C1 V1 plus C2 V2 plus et cetera, plus Cn Vn, right? We had this definition when we had vectors in Rn, right? But now we're just looking at an arbitrary vector space, V. What's a spanning set? Well, it's the same thing, but we need to define it for an arbitrary vector space. The span of V1 through Vn is the set, and we'll write it as span V1 through Vn. And this is going to be the set of vectors V in your vector space such that V is equal to a linear combination of elements in this set here, this V1 through Vn. So this would be like Ci, Vi, and we would also have for Ci in the reals, right? So the notion of a linear combination and the span, it's the same notions, right? Now we're just taking a more general approach because we're not looking specifically at vectors in Rn, we're looking at elements of an arbitrary vector space. Okay, so pretty easy to understand the definition since we've already done so much of this for Rn. And what's the most important here is, well, of course, that we understand the definitions, but also that we can see some examples for vector spaces that aren't necessarily Rn, right? So let's look at some examples here. Let's say we are going to look at V is going to be the vector space M22, which this is, remember, all 2x2 matrices. Now, let's let A and B, these will be elements of the vector space M22. And we want to ask, well, first let's define what A and B are, right? We have A is given by 1, 0, 0, 2, and then B is given by 0, 1, 1, 0. And we want to ask, are A and or B in the span of the following the following elements of our vector space here. We'll let M1 equal 1, 0, 0, 0, and M2 is going to be 0, 0, 0, 1. Okay, and so the question is, A, B, an element of the span of M1, M2? Question, right? That's what we're asking here. Well, what does it mean to be in the span of a collection of elements of a vector space? It means we can find constants such that A or B can be written as a linear combination of M1 and M2. So let's start with A, right? We're asking for A, which is 1, 0, 0, 2. Does there exist constants, let's say K and L, such that we can write K times M1, which is 1, 0, 0, 0, plus L times 0, 0, 0, 1, right? This was M2. If there exists K and L that make this equality hold, then we know A is in the span of M1 and M2, right? Pardon me. So let's see what we get here, or see if this is possible. Well, let's start with our scaling these matrices, right? We're working within a vector space, so we know all the axioms of scalar multiplication and vector addition are satisfied. So here we have like K 0, 0, 0 plus 0, 0, 0, L. And this is going to be K 0, 0, L. And you can see this equality holds when K equals 1 and L equals 2. This has shown the existence of constants, such that A is a linear combination of M1 and M2, which implies that A is indeed in the span of M1, M2. But what about B? Well, let's check. B was 0, 1, 1, 0. And so now we're asking, does there exist K and L such that K is or such that B is equal to K times M1 plus L times M2? We go through the same process here, and you would get K 0, 0, L. And now this can never hold, right? Because for two matrices to be equivalent, every entry has to be equivalent. And we have here, what we've said is for the anti-diagonal here, we have that 0 equals 1, right? This is an inequality for all K and L in R, which implies that B is not in the span of M1, M2, right? So there's an example in the vector space of matrices, of 2 by 2 matrices. Let's look at an example in the vector space of polynomials of most degree 2. Let's show. So here's a new example, right? Let's show that the polynomial, or the element of P2, 7x squared plus 4x minus 3, is in the span of elements 4x squared plus x and x squared minus 2x plus 3. Now, to show that this is in the span, we have to show that 7x squared plus 4x minus 3 can be written as a linear combination of elements in the spanning set, right? Or that constitute the elements that we're looking at the span of, rather. So this means we're asking, does there exist K and L such that 7x squared plus 4x minus 3 is equal to K times 4x squared plus x plus L times x squared minus 2x plus 3. Well, let's see if this is possible. Then we have distributing, we get 4k x squared plus kx plus lx squared minus 2lx plus 3l. Grouping like terms here, it looks like we're going to have 4k plus lx squared, and then plus k minus 2lx, and then plus, looks like the only constant term here is plus 3l, right? And now two polynomials are equivalent if and only if the respective coefficients are equivalent, right? Meaning the coefficient for x squared has to be equal to the coefficient for x squared. And so because of this understanding, we get the following system of equations, right? Well, equating the x squared coefficients, we know that 7 should be equal to 4k plus L. Equating the linear coefficients, we have that 4 should be equal to k minus 2L. And then for the constant terms, we have negative 3 equals 3L. Well, luckily, this system is easy enough. I don't think we need to set up an augmented matrix or anything. So this gives us L is negative 1. plugging in L is -1 back up to the top gives us that 4K equals 8, which implies K equals 2, which means that 7x squared plus 4x minus 3 is equal to 2 copies of 4x squared plus x minus 1 copy of x squared minus 2x plus 3, which shows that this element is in the span, right? So 7x squared plus 4x minus 3 is therefore in the span of 4x squared plus x, comma, x squared minus 2x plus 3. Okay, I want to do one more example. Excuse me. I want to do one more example of looking at spanning sets for arbitrary vector spaces. This one, again, is going to be in the vector space P2, right? And let's show that the span of x squared plus 1, x minus 2, and 2x squared minus x is the same as P2. And if you'll remember, I'll kind of hint at where we're going to go from here is this means these are isomorphic as vector spaces, right? We remember that a spanning set is in a one-to-one correspondence of subspaces, right, of a vector space. And if two subspaces are equivalent, that means there exists an isomorphism between them, right? And so there's a notion of basis elements in a generalized vector space as well, right? And you would have that these are basis elements. And we'll go on to show linear independence, right? We have to show that remember, a collection of vectors is a basis if it's a spanning linearly independent set. So one way you could show this is the same is find an isomorphism of basis elements. But we don't really have that vocabulary or understanding yet in the context of a generalized vector space. So what we can do is just show that any element of P2 must be able to be expressed as a linear combination of these elements. So let's let P2, this is going to be, we'll write, an arbitrary element of P2 would be ax squared plus bx plus c, right? Now, to show that this, any element is in the span of these three elements here, what we have to do is find k, l, and m such that k times x squared plus 1 plus L times x minus 2 plus m times 2x squared minus x holds for some values k, l, and m. But we have to figure out what those are, right? Well, let's expand the right-hand side here. We're going to get kx squared plus k plus lx minus 2l plus 2mx squared minus mx. And then if we group like terms here, it looks like we're going to get k plus 2mx squared, and then plus l minus mx, and then plus k minus 2l for the constant term. Now, what do we have? Well, again, remember, a polynomial is only equal if all of the coefficients for each degree or for each term are equal, right? So this means we have that a is equal to k plus 2m. We would have that b is equal to l minus m. And then we would have that c is equal to k minus 2l. Right? And so here what we have is we have a, b, and c solved for in terms of k, l, and m. But to show that k, l, and m exist for any a, b, c, we have to write K, L, and M in terms of ABC, right? So basically, what we need to do is solve this system of equations for K, L, and M in terms of A, B, and C, right? Well, how would we do that? We would do that by setting up an augmented matrix. We would have K, so for the first equation, the coefficient of K is 1, coefficient of L is 0, M2, and that's equal to A. And then we'll have 0, 1, negative 1, B, and then 1, negative 2, 0, C, right? And to see if this does have a solution, or if there do exist K, L, and M in terms of ABC, you put this into reduced row echelon form, and I'll leave that as an exercise. And what you get is 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 1/2 A plus 2B plus 1/2 C. And then that looks like 1 over 2C, but it's not, right? That's 1/2 C. And then we have 1/4 A minus 1/4 C. And then we have 1/4 A minus B minus 1/4 C, which implies that K is equal to 1/2 A plus 2B plus 1/2 C. L and M, we have L is equal to 1/4 A minus 1/4 C, and M is equal to 1/4 A minus B minus 1/4 C. So for every element of P2, there exists K, L, and M such that AX squared plus BX plus C is written as a linear combination of these three elements, right, that we're looking at the span of. So this shows that P2 is indeed the same as the span of these vectors here. Okay, so there was some examples of what spanning sets look like for an arbitrary vector space, or how it's defined, and then some explicit examples. In the next video, we're going to do the same thing, but this time look at linear independence as a notion in general vector spaces.